Alright, so in a previous video we established the very basic circuit model of the DC machine, separately excited DC machine that is. Now in this video what we're going to do is we're going to take what we learned in that video and we're going to take it one step further in order to understand how the speed of the machine can be controlled in different ways. So if you recall from that video, and if you haven't seen it, I'll link it in the description below. If you recall from that video, we said that the steady state conditions were such that VA was not equal, it was approximately equal, is approximately equal to K phi omega m, and we said that Tm, the torque, was equal to K phi Ia. Now if you combine these two, you get an expression which says omega m is equal to VA over K phi minus Ra over K phi squared Tm. And this is the torque speed characteristic of the separately excited DC machine, the circuit that we saw in the previous video. Now, some things to note here. This is the no load speed. So this is no load speed, which is obvious. If Tm is 0, that means there's no load. That means there's nothing connected to the end of the motor or the machine. If that's the case, then this term goes to 0, and this term is all you have left. And this here is basically the decrease or the change in speed due to the change in load torque, which is essentially a slope. So how do we visualize this? Let's take a look at this this plot, and let's put here Tm, and let's put here omega m. And if you start here from some no load speed, let's use a straight line like this. So you start with some no load speed like that, and I'm going to use multiples here because it'll illustrate the concept, I guess, a bit better than if I just use a single one. So let's use a green one, and then we can use another one. And this can be pink, let's say. So what happens in this case is you have this, well, let's use pink, and then I have to go select, tap there, and then bring this back. And this is increasing VA. So as you increase the armature voltage, these curves will move up. As you decrease it, it'll move down. Of course, this is the VA over K phi, because that's when the torque is equal to 0. And of course, the slope in all of these is equal to Ra over K phi squared. Okay, so this is referred to as speed control by armature voltage. So we say speed control by armature voltage. Why? Because you can control the speed by the armature voltage. How? Increased VA and the speed goes up, decreased VA and the speed goes down. Fairly straightforward, not a whole lot really going on there. I mean, we're just doing it based on whatever we see here, plotting different curves. But we're trying to build the motivation as to why we're going to do things the way we do. So the next thing we can do is we can look at the other variable. I mean, what variables do we have that we can actually control in this equation? Tm is dictated by the load. Ra is a property of the winding. You can't control Ra. You can control VA, and you can also control K phi. Because remember, K phi is equal to Kf times If, right? So that's the field current. So using that knowledge, what you can do is you can have a similar plot of omega m by Tm, and you can plot these, you can plot similar lines, but the relationship between these lines will be different. So let's say you have one that looks something like this here. Let's say you have one line that does, well, I keep forgetting to hit escape after I drop lines. So you have another line here. Let's say this one does something like this. And then let's say you have another line. Let's make this one yellow. And let's say this one does something like this. I don't like that because it's not very slanted, is it? This one's a bit better slanted. Okay, so we can I mean, since they're all in color, we don't really need to number them 1, 2, and 3, I guess. But I guess we can just for the sake of consistency. Let's call this 1. Let's call the green one 2, and then that means the blue one will be 3. Okay, and in this case, you have k phi 1. You have which is related to if1, and then you'll have k phi 2, which is related to if2, and then you'll have k phi 3, which is related to if3. Now the relationship between these is that this is larger than that, and that's larger than that. How do we know that? Because the slope dictates that. So a smaller k phi means a larger slope, because it's in the denominator here. So if this is smaller, this slope is larger. This is exactly it. So now what we can do is, this is another way we can control speed. So we can say that this is speed control by field current, right? So now we can control it by the field current as well. So now what we can do is, I mean, the best, I guess, option would be to control it using both. Why not have a combination? So we're going to combine these two in a plot, and I guess since we're using shapes and such, why not just use this shape tool and make this shape here? Seems like a good idea. I guess we'll see how that goes. What are we doing now? We're going to plot something here, and we're going to call this the resistance. Okay, so this is the resistance. And what I mean by resistance is it's basically a load. And this here will be Tm. This here will be omega m. Now every, let's say 5, let's use 5. Let's see how many we can get with 5. So every 5 blocks, I'm going to create a sort of new boundary type of thing. 5, that is also 5. And I only need 4 of them, so we're okay. So I have here, we'll call this omega 1, we'll call this omega 2, we'll call this omega 3, we'll call this omega 4. So what are we trying to achieve here? We're trying to show what the torque speed characteristic would look like in order for us to meet these speeds. So what I mean is, if I have a machine and I want it to operate at these different speeds, omega 1, 2, 3, and 4, it will have a certain profile that will require it, that'll basically, like, it'll follow a certain profile, something like one of these two, in order for it to hit that speed at that certain resistance, right? So for instance, what does that mean? That means if I have a line that looks like this, for example, and this is just an arbitrary argument, that it'll look something like this, right? And if it starts from this no load speed at some condition, it'll hit the resistance, that load condition there, whatever load operating point is. So this is like an operating point, essentially. It'll hit that operating point at this speed. But if I'm operating at that point and I need a different speed, something has to be adjusted, right? Whether that's the armature voltage. If I increase the armature voltage, it would move up like this, let's say. And then I would be able to hit that curve there. Right? So what we're trying to do is we're going to look at a bunch of different, or we're going to look at different cases, and we're going to look at how these profiles can kind of be adjusted based on whatever conditions you need. What I'm going to do is I'm going to draw some line that looks fairly arbitrary, which I will repeat. So that's the line. And I'm going to say that this is the intersection of the first one, and we'll say that this is the intersection of the second one, and this should be a different color. And then I want to say, let's have a third line. Well, let's just use the exact same line to illustrate our concept, because we're trying to keep the slope consistent for these three. And now what I want to do is I want to create another line here, like so. And this line should intersect here. But I'm going to make this one red for a reason. And what else do I want to do to this? Let's leave it red, and maybe we can even make it a dotted line instead. So why don't we make this a dotted line? try to keep the same slope as the previous. Well, another easy way to do that, I guess, would be to do this. So if we do this, just draw over it. It's important that we keep the slope of this line the same because it's illustrating a very important concept. So this is that dotted line, and I'll explain in a second why it's important. But this is that dotted line, and then I'm going to draw another line, and this line that I'm going to draw will be what? Let's make it white, because it's the ultimate kind of, not the ultimate line, but it is the one that proves the point, I guess. For that reason, it will intersect here as well, but it will do so with a different slope. Let's say it's something like this. There. So this is not going to let me intersect properly, is it? But we'll assume that it's intersecting properly, and we'll put a big dot here so that everybody knows it is intersecting properly. We'll put dots here as well, just so that everybody knows that these are all points of intersection. Now, what's happening here? Let's label these lines 1, 2, 3. Let's call the red one 3 prime, and let's call the white one 4. So, in all of these, 1, 2, and 3, you basically have what we call a full flux and an armature voltage below the maximum. So when you apply a field current, you produce a flux, and there's a certain amount of flux that the machine can tolerate in order for it to still be in the linear region, and in order for it to not be saturated, in order for all the materials to operate as they do properly, because there's a certain field you can produce. If you can only produce a certain field or a certain strength of field, you can only have a certain amount of flux. So these conditions here, omega 1, 2, and 3, I guess we can label here, and we can call these, let's use this color here, so we can call these all full flux and armature voltage below the maximum, right? So let's say that's 1, 2, and 3, right? So let's say this region here, let's go from here and here, I guess. So say here, and we can say full flux and VA less than VA max, okay? And again, this VA max is a concept. This is conceptual. There's no numbers here because this is a concept, right? So this is why we're doing what we're trying to do. At this point, so at this speed, I guess, or this profile, or in this region, I guess, if you even want to say that, or this curve, or this profile, I guess, yeah, let's say profile, let's say. So this profile has full flux conditions, so it's the maximum it can handle, and VA is also the maximum it can handle. Now, at this point, you have full flux, so 3 prime is full flux, but this is excessive armature voltage. Because remember, these are machines, these have ratings, and therefore they can only operate up to a certain, you can't connect like a 100-volt machine to like 500 volts. You would ruin the machine. So there's a certain limit. That upper limit gets reached, and now you have excessive voltage, and you can't have that. So how do we address this issue? We address this issue by increasing the armature voltage increases the point where you hit this y-axis, right? So as you increase armature voltage, you would hit different points. If you, instead of hitting it at a higher point, you start at a lower point, but just decrease it less as you go here, it's essentially a lower slope, right? So what that means is, if I were able to extend this white line all the way up, and I were able to extend this dotted red line all the way up, they would intersect somewhere. That would be whatever no load voltage or no load speed I need in order to reach this at this resistance rating. Instead of giving it that armature voltage, what I'm going to do is I'm going to say give it a lower armature voltage, but just decrease it decrease the slope at a different rate. Now, in order to achieve that different rate, what I do is I apply something that we refer to as field weakening. And what that does is that says this is max VA and reduced flux. So I reduced the flux. And what does reducing the flux do? It reduces the slope. And it means it drops off at a lower rate than the other ones do. So the white line is obviously a smaller slope than the green, the blue, and the pink. This is what we refer to as called field weakening. So suppose we want to go up to this omega 4. We can achieve this by increasing the armature voltage up to whatever it is at omega 3. So up to this point we're okay because we have a maximum rating there. We get up to omega 3, we say the armature voltage then hits its ceiling. So if you want to increase this speed omega 3 to omega 4, what you need to do is you have to reduce the flux K phi, because you can't increase VA any further. So you decrease K phi to increase, well, I guess to decrease the slope of the characteristic. It depends which way you're looking at it. In this case, you're decreasing the characteristic, but in the other case, I mean, it depends which way torque and how the two are torque and speed are related, whether they're on the X and the Y. But in any case, you want to adjust the slope, let's say, so that it meets the resistance at omega 4, and we call this field weakening. So, what can we summarize in this situation? We can summarize the following. We can say that VA1 is less than VA2 is less than VA3, which is less than VA3 prime. And we say that this is max VA. And we say that this is violation of VA limit. And we say also, I guess we can make another note that VA4 is equal to VA3, because when we get to the end here in 4, we're actually using the maximum, which is this one, but we're just adjusting the actual slope. So that's it for the discussion of speed control. We've seen conceptually how this can be controlled. Now in upcoming videos, what we'll do is we'll look at how you can implement this based on the requirements of the torque, based on the torque speed characteristic of the vehicle, how we can use this to match those types of profiles. And so again, this was based on the previous video steady state model. Was not very much derivation here, but this was more of a conceptual analysis, which is very important when we're trying to understand how these machines, how we can control them and how they operate. So we saw how the armature voltage can increase the no-load speed here, and we saw how the field current can basically adjust the slope, and then we saw how the combination of the two can be used to achieve different speeds at different operating points. And in the following videos to come, we'll see how we can use all of this to control the speed and torque of a DC machine in order to achieve the characteristics we want in our vehicles. So I hope this was helpful. Like and subscribe to support the channel, and we'll see you in the next one.